So, welcome to module 2. In this module, we will be talking about storage hierarchy, exceptions, interrupts and traps. These are concepts that are extremely important for one to understand the functionalities of the operating system. Operating is something we expect from the operating system. We want it to do certain managements, management of process, management of files, management of memory, etc. To understand these functionalities in good depth, we need to understand certain terminologies which are very important. Namely, we need to understand what we mean by storage hierarchy, what do we mean by exceptions. Exceptions is of two types, interrupts and traps. So, in module 2 we will cover these things in detail. When you look at a traditional computer system organization, so you basically have a bus which is given by the lines there, and then you have a memory, then you have a CPU, and then you have a set of peripherals. On the screen you see 5 peripherals, namely the disks, the mouse, the keyboard, printer, and then a monitor. Each of these peripherals have certain intrinsic value in terms of, suppose we take a disk, there is a way a disk will store certain data, there is a way the disk will allow access to the data. So, different disks could have different formats. Similarly, different printers could have different formats by which they will do the printing, they could have different functionalities. Now, between the disk and the bus, as you see there in the slide, there is a disk controller. The disk controller understands the language of the CPU and also of the underlying peripheral, namely the disk. So, the disk controller can be termed as an adapter which adapts the functionalities required by CPU to be carried out on the disk. It basically translates the need of the CPU to a language understandable by the peripheral it controls. So, for the disk we have disk controller, similarly for the monitor we have a graphics controller or graphics adapter, and for the mouse, other IO devices we also have this USB controller. So, the CPU can communicate to the peripherals through the corresponding controllers, and note that these controllers are basically hardware, they sit between the bus and the peripheral. Now, these CPUs, they actually work concurrently with the devices. So, when a disk is actually performing certain activities, the CPU can also start doing some activities, and both of them clash when they need the bus. So, the bus itself is a shared resource which needs to be scheduled. Term scheduling means that a particular shared resource is allocated to one of the entities which request for using the shared resource at a particular point of time. So, the bus itself is a shared resource and that needs to be scheduled properly, and the IO devices basically need to talk to the CPU. The IO devices also need to talk to the memory. So, there are different ways by which an IO device can communicate. The data from an IO device can be moved back and forth from the system. For example, if the CPU wants to directly read from IO device, each of these controllers could have a local storage. So, the IO device can basically write into this local storage and then give an interrupt. An interrupt is nothing but a signal to the CPU that I have some data available to you, why do not you take and use it. So, who will inform the CPU? The device controller will inform the CPU. If, for example, the keyboard wants to talk to the CPU, then through the USB controller it can basically send an interrupt to the CPU saying that it has some data which the CPU can use. Now, the CPU will be responsible for taking that data from the device controller and basically using it. There is another way by which data can be transferred back and forth from the system, and that is through the memory. So, later in the memory management we will look at something called DMA, which is called direct memory access. So, when a peripheral wants to send data into the system, it would, for example, if I want to transfer a file, we will transfer the content of the file from the disk to the memory without involving the CPU. So, the term direct memory access, what do you mean by direct? The term direct essentially means that I am bypassing the CPU. So an IO operation can also happen between the peripheral and the memory without the CPU involved, and this particular operation is called direct memory access. So to sum up what we have seen, the organization of a typical computer system would be a bus. On the bus, the CPU will be attached to, the memory will be attached to, and there will be peripherals, and each of these peripherals will have a controller which is hardware. Now the CPU talks to these peripherals and vice versa through this hardware controller, and this is how a typical computer system is organized and the IO operations take place. Now coming to the storage, storage is actually one of the major innovations in computing. This allows you to write something and remember something, right. So the time that I could remember actually is something very, very important. For example, if I store my whatever I would want to remember inside my CPU, then I could access it very, very fast. If I store it outside the CPU, the time required to basically retrieve what I have stored will take little more time, so it will be higher. And then I want to permanently store something, then I store it in a disk. What do you mean by permanent? In the sense that I want to store it till I want to delete it. So even if I switch off the system, the data will be stored and I could retrieve whenever I switch on the system. So this is basically called volatility, right. So if I store it inside the CPU or in the main memory, which we call as the random access memory, when I switch off the power, the data gets lost. So these are all volatile storage. But if I go and store it in a disk or something more there, as you see in the slide, if I had to store it on a magnetic disk or an optical disk or magnetic tapes, after I switch off the power, still whatever I have saved will be there and I could retrieve at any later point of time. So those storages are called non-volatile storage. So as you see, we have registers, we have cache memory, we have main memory, then we have electronic disk, then magnetic disk, optical disk and magnetic tapes. The last four, namely the electronic disk, magnetic disk, optical disk and magnetic tapes, they are non-volatile storage, while the main memory, cache and registers are all volatile storage. Now as I go down the hierarchy from registers to magnetic tapes, the amount of time I spend to basically store a data and retrieve it back, to read and write from that memory, this time actually increases. The time I require to read and write from a register would be very fast, it will be in nanoseconds, and also in cache it will be say tens of nanoseconds. Main memory could go more than the nanoscale. But when I go to electronic disk or magnetic disk, optical disk, magnetic tapes, this could be several orders of magnitude slower. So we are looking at volatility and going towards non-volatility as we go from top to bottom, and again the speed of access, basically access means read or write from a particular storage entity. The time for access actually increases in a very fast pace as we go from registers to magnetic tapes. But on the other hand, the cost per bit, I want to store what is the cost I incur to create one bit on a register, to create one bit on a cache, to create one bit on a main memory and so on and so forth, the cost also decreases. So this is how the storage hierarchy is built in a computing system. And one of the important things that we should note here is that at every level I would have something called a cache memory. The cache memory that traditionally we see is the cache memory that is inside a chip or inside a CPU, but even for file systems there is something called buffer cache. Even when you download through the web, your browser has a browser cache. What do you mean by this cache memory? Is that I am retrieving say from a electronic disk onto the main memory, and I am writing it back. I am retrieving something which I am using it quite frequently. So, instead of every time going to the electronic disk, I will take some amount of data and keep it in the main memory and reuse that in the main memory, and at a later point of time store it back into the electronic disk. So, every time I need not go to the electronic disk, I will create some locations in the main memory and keep using it. By this, every time I want to access a data, I access it from main memory rather than the electronic disk. By this, my speed of access actually basically increases here. So, at any level, a cache is something which will take the data from the level below it and keep it for reuse, and at a later stage will send it back to the lower level. So, this is the notion of the cache. So, as we go through the operating systems and networking, we will find lot of places where cache memory caching as a concept is being employed, basically to improve access times, and that is also very important for us to understand in the context of storage. The next important thing is the I/O in a computer. So, everything is basically I/O. Today I use a mobile phone, I use a laptop, I use a projector. Now you are viewing this course over a web. This is all input output operations. So, we need to understand how I/O works in a computer, and please also note that all we are talking from a security point of view. All the access that comes, all the sort of vulnerabilities that we see in practice also basically depends upon the I/O, the strength of the I/O, the security strength of the I/O mechanism. So, for us to appreciate I/O in its full, let us understand some of the important aspects of input output operations. The first thing is a synchronous I/O. What do you mean by a synchronous I/O? I am a program in execution and I want to do an I/O operation. I start the I/O operation and I do not proceed till that I/O operation is completed. So, I actually wait, I idle in the CPU till that I/O operation gets complete. So, this is basically called a synchronous I/O. By doing this synchronous I/O, at most one I/O operation can be initiated, and after it completes, the next I/O operation can happen. In the case of an asynchronous I/O, the program in execution, which we call as a process, the process that actually wants to do this I/O operation basically starts this I/O operation, it comes back and it starts doing other useful work. At some later point of time, there would be an interrupt from the device saying that it has completed, then it will go and check whether it has completed, and it will take some necessary action depending on whether the completion was successful or unsuccessful. This is basically called as asynchronous I/O. By doing this asynchronous I/O, a process can initiate an I/O operation, and when that I/O operation is basically happening, then it can do other useful work. By this, we through asynchronous I/O operation, the computation and the communication can be sort of done in a concurrent fashion. So, asynchronous operation crucially depends upon certain things like a system call. What is a system call? It is a request to the OS to start an operation, and sometimes it is a request to an OS to make the process wait till an I/O is completed. So, the typical way an asynchronous operation would happen is, there are typical system, there would be more than one processes that are executing at a point of time. So, there will be process 1 that is executing, there will be another process 2 that also wants to execute. Now, when process 1 starts executing, it will execute on the CPU, then it will come to a stage where it needs to do an I/O operation. Then immediately it tells the OS, I want to do an I/O operation, and till the I/O operation is completed, please suspend me. So, the process is actually blocked and the I/O operation will start happening. And when the I/O operation is happening, the CPU is not involved in that I/O operation. So, the CPU can start working on the second process which is waiting for it. And once the I/O operation is completed, then an interrupt comes to the CPU saying I/O is completed, then the process 1 which is waiting for the I/O to complete can start working again. So, this is also a different notion of asynchronous communication, where a I/O operation and a computation can happen concurrently. Now, system call is a way by which a process, which is nothing but a program in execution, will request the OS for certain services. And a typical operating system will also maintain something called a device status table, which is maintained for each IO device and which will contain information or attributes about the device, its type, the addresses to which it is mapped and state. And this is organized as a table. So, depending on the device, every device will be given an ID or an index, and the OS will actually index into the table using a device ID and go and find about what is happening with the device. So, this is how IO in a computer is basically managed. So, we need to understand what is a system call, we need to understand what are device status table, and even from a security point of view, understanding of these concepts are very important, because tomorrow attack actually happens when we look at the secure aspects through these system calls, through certain loopholes in these system calls, and by manipulation of some of these shared tables, including device status tables. So, these are some of the things that we need to keep in mind and understand. Now, we will understand very importantly what we mean by an interrupt. All the operating systems today are interrupt driven. Suppose you take a mobile phone, the mobile phone is dormant. When you press a key, then the screen comes up. When you touch the screen, then something happens. So, the mobile phone is actually an example of a reactive operating system. It reacts, or it reacts to an event. So, sometimes it is also called event driven operating system. Sometimes it is also called an interrupt driven operating system. Almost all the OS that you see today in practice are interrupt driven operating system, because when I go and touch the touch screen, please note that there is an interrupt that is generated and then certain actions are being done. Now, what is an interrupt? Interrupt is actually an asynchronous signal indicating the need for attention. An interrupt can also be a synchronous event in software indicating the need for a change in execution. So, when we do some aspects of process management, we will understand about asynchronous event, which we call as interrupt, and synchronous event, which we call as interrupt. Now, in the next slide we will see a little more. I would like to go to the next slide before coming back to this again. Different books have different terminologies, but for the purpose of this course we will understand interrupt as follows. There is something called an exception. What is an exception? An exception is a request for some service from the CPU, right. So, who is generating this request? The CPU is generating this request. Now, what do you mean by a CPU generating this request? The CPU has found certain exceptional scenario. What is an exceptional scenario? Exceptions are of two types. One is called trap, another is called interrupt, right. So, many books have different terminologies for this, but for the purpose of this course, this is the terminology I will be following. There is something called exception. Exception is something like an exceptional scenario that is the CPU has encountered, and it is requesting for some attention from the operating system. This exception is of two types. Type 1 is called interrupt, type 2 is called trap. Trap is something that I, as a program in execution, have created an exceptional scenario. For example, divide by 0. Whose mistake it is? It is the program's mistake. The process that is in execution, it has done a divide by 0, it is trying to do a divide by 0, and hence exceptional scenario has come up. Segmentation fault. If you look at my information security 2 course, architectural light information security, we have talked elaborately about segmentation fault. We have talked about interrupts and exceptions also there in very great detail, right. So, I try to access a segment, I as a process program in execution try to access a part of the memory which is not intended or allocated to me. This is called a segmentation fault. So, who is responsible for it? The program that is in execution is responsible for it. So, those we call as traps. Suppose a disk has finished operation, or in the keyboard I go and press a Control C, or in the keyboard I am just going and changing the slide, for example like this. Now, these are all exceptional scenarios that are coming from outside the system, outside the CPU, created by the IO peripherals or the external hardware. So, any request for attention, or what we call as an exception, comes from outside the CPU, that we call it as interrupts. So, exceptional scenario is a scenario where there is a request by the CPU for some special attention by the operating system. This exceptional scenario can be of two types, one is called interrupt, another is called trap. Trap is something that the program in execution within the CPU has generated an exceptional scenario for which an attention is requested for. An interrupt is something external to the CPU chip, which is coming from external peripheral devices, etc., that you need to handle, right. So, all the modern OS, as I mentioned, are actually interrupt driven. Now, let us go and see how these exceptions are basically handled, right. Now, what happens when there is an exception? Every exception, whether it is a trap or an interrupt, has a number. So, when there is a number that is given to this, now there is a table called an exception table, which we call as an interrupt table. For every exception, there will be a pointer to a code which needs to be executed for exception. For example, if I do a divide by 0, then I go to the interrupt table will tell, for example, the divide by 0 will be allotted a number, say 10, then we go into the interrupt table, and in the 10th location in that interrupt table, we will basically have a pointer or an address of a particular code. If you go to that address then and start executing the code starting at that address, then it will be the service for the divide by 0. Basically, it will print on your screen divide by 0 error and it will terminate. So, for every interrupt there is a number, and when that interrupt is generated, the hardware automatically goes to the interrupt table and index into that interrupt table with that number, and in that entry there is going to be a pointer to a code segment or a code, and that code will start executing and that code will do the necessary service. That code is called the interrupt service routine. So, a very detailed way of how the Intel architecture handles interrupts and exceptions, traps and interrupts, namely the exceptions. This has been covered in the Information Security 2 course. I request the audience to look into that course, that module in that course. It is available on the NPTEL site to get more on this. Actually, the second course, we have even written an interrupt service routine from scratch. So, before we proceed, let us look at these definitions. I have been repeating these definitions. What is a process? It is a sequential program in execution. What is a resource? It is something that a process can request. A process can request for a CPU time. Yes, it is a CPU time is a resource. The process can request for a peripheral, so hence it is requesting for a bus. Bus is a resource. Process can request for some memory location by saying I want to read or write into a particular memory location. The memory location is a resource, and when that resource is not available, for example my CPU is not available or my peripheral is not available, the process can be basically blocked. So, if I am blocked means I cannot execute further till, because I need a resource and that resource is not available, the operating system can go and block me and then allow me to proceed once that resource becomes available. File is actually a special case of a resource. It is actually a very broad definition of a file is a linearly addressed sequence of bytes, or what you call as a byte stream, right. So, we will be looking into files also in great detail. So, to sum up, if I look at OS, the organization of an operating system, which is very important for us to later appreciate the secure aspects of operating system design, is that there are two layers. One layer that you see in the bottom, as you see on the slide, is the real hardware. I have processors. Today I have multi-core environment. I could have multiple processors there. Then there is a main memory, and then there are devices. And different modules in the operating system governs each one of them. For example, if you look at a traditional operating system, conventional operating system, even modern operating system, there is a module which is called process, thread and resource management module manager, and that is responsible for handling the compute part, namely the processors. That is responsible for what you call as CPU handling or CPU scheduling handling, etc. Then there is a memory manager which basically handles the main memory, the RAM, and there are device managers which basically has device drivers etc., which manages the devices, and all of them basically uses the files. What do I work on? I work on a file. Please note that if I want to store any information in the computer, I can store it only in the form of a file. So, a file is the basic unit of storage in the operating system. So, the memory manager, the device manager and the process thread and resource manager, they basically talk to the file manager to get lot of information from the files. So, the memory manager also talks to the file manager, the device manager also talks to the file manager, because lot of file related activities happen at the memory. I just mentioned about something called buffer cache that is maintained in the memory, for example, and lot of things about files also happen in the device level, because when I want to read a file, I just say read that file, then which part of the file, from where to read, where it will be located, everything basically there is happens, the entire read operation happens in a very synchronized fashion, where the file manager and the device manager are deeply involved. So, to broadly tell, so now that we have an understanding of the operating system to some reasonable extent, these are all some of the services that are expected out of an operating system. The operating system is a very big software. Now, to understand operating system, we will take a modular approach, wherein we will break this software into small components and they start talking to each other. Already we have seen partition of the different modules in the previous slide, as I am just projecting it here. So, we have at least 4 managers managing 4 important aspects of the operating system. Now, many modern operating systems have these 8 management modules, namely process management, main memory management, file management, IO system management, then secondary storage management, networking, protection system, command interpreter system. So, these are all different components of an operating system, and we will see that in better detail in the next module. Thank you.